Hello everyone, myself Girish with SolidWorks Flow Simulation Tutorials. Today I'm here with the new topic, that is Introduction to Internal Flow Analysis. So in the previous sessions I have gone through Introduction to External Flow Analysis and even the basics of SolidWorks Flow Simulation and the CFD or CAE CFD interview questions and all I have covered in the previous sessions. You can go through that. Okay, so in this we'll see three examples. One is finding out the uh, gauge output velocity and even finding out the pressure difference between multiple output if you are having. Okay, and then finally in the third case study we'll have a look on how to deal with the pressure drop analysis by using the a simple valve uh, taking into account and running the SolidWorks flow simulation. Okay, we'll have a look on the nozzle here. We'll take the case study of nozzle. Okay, we'll give the inputs like fluid. We'll consider water. Okay, this kind of sprayer nozzle you have seen in washrooms and all, right? Yeah, so I'll define the inlet pressure of 4.5 atm. Okay, and then outlet pressure, it is 1 atm, that is environmental pressure will define. Okay, by taking these inputs into account, we'll find out how this nozzle behaves and what is the average velocity at the output. Okay, we'll jump into the SolidWorks now. Yeah, here you could see the nozzle model. Okay, the input and the output has been defined and the lids has been automatically created by using the SolidWorks Pro simulation. Okay, I'll take this section view to just showcase how exactly the model has been generated with the inlet cutouts. You could see there. So the top knob will help us to stop or regulate the flow inside the nozzle. Okay, so by adding the flow simulation from the add-in, you can have this flow simulation tab, and from here you can use the new wizard to define the study. Okay, I'll define the unit system. I'll keep it as degree Celsius remaining as default. I'm not gonna change anything here. Okay, the flow is internal as you already know. Okay, and then remaining everything is fine. If you want to activate the gravity, you can do it. I'll keep it as it is now. If you are looking for heat conduction and all, you can activate. Radiation is there. If it is there, you can activate the radiation as well. Okay, so what exactly this exclude cavity does is it will exclude the extra cavity if is there, like if any extra cavities are there inside. So now I'll select the water as a fluid medium from the liquids. So we have the flow type laminar and turbulent. I'll keep it as default because software automatically select as per the Reynolds number. Okay, the wall conditions, I'll keep it adiabatic, there is no friction, and the wall boundary conditions. Okay, and the pressure and temperature, will keep it as it is as per the room temperature. I'm not gonna change anything here. Okay, so according to that, the software will create the computational domain with respect to the cavity. Okay, now we'll directly jump to the project, and here in the inputs I'll define the computational domain. So this is fine. So if you want to manually edit it, you can go ahead to edit the parameters. Now I'll just go ahead with the input parameters, that is boundary conditions I need to define. So here I'll select the static pressure of 4.5 atm, okay, as the input pressure, and this phase is the reference. And then I do need to define the outlet condition. I'll go ahead with the boundary condition, and I'll select the phase as a reference, and I'll define the environmental pressure into account, that is 1 atm. I do need to select the phase, so this is the reference, okay, for output. Yeah, so once you define these things, you can directly go ahead with the goal definition. I'll define the few of the global goals. Okay, the first one is the mass flow rate. and remaining, if you want, you can add it. For now, I'll select this surface goal. On this face, I need the velocity to be taken into account, so that is average and maximum. Well, so meshing part, there are two methods. One is automatic and the manual. So here I'll keep it as default and I'll run the study. Okay, here just we are analyzing how to just get the results according to the goals we require. Okay, once you run the study, you're gonna get the results here. So we will take some time to just give the results. Okay, it might be a few iterations. So once the results gets converged, the output tool will stop the entire process and it will go ahead with the post-processing stage. Here the cut float. So I'm selecting the velocity float. As you could see at the outlet, the velocity is more and the value is 30.71 meter per second. Okay, if you want to customize it, you can set it to original default, and according to that it will just customize your study. Sometimes this will happen. Okay, everything is right, so that time you just need to reset your floats. If you want to change the float, you can simply use this drop down, and from here you can activate the different floats. Okay, this is the pressure float, how the pressure is varying. And then if you want to check the flow trajectories, you can use the flow trajectories, and here you can select the input phase into account, and accordingly you could see the flow trajectories. If you want, you can animate it. So these are the pipes. Actually, if you want to change it, you can go ahead with the options and change it. So according to the cut floats, the flow trajectory will also update. Okay, so here I'll just change it to, instead of pipe, I'll choose the arrows. If you want, you can reduce the size. Okay, yeah, so this is how it is. And now if you want to animate this, you can simply go ahead with the play option to just see how exactly the flow is happening. Okay, yeah, so this is the simple funda about the internal analysis. So here we have just gone through the boundary conditions and we have just checked each and everything. So finally the goal plot. So you could see the average and the mass flow rate as well as the maximum velocity. Average is 20 and the maximum is 30 meter per second. Okay, so if you want to cross check the results in the form of graphical representation, you can use the drop down and do the same instead of switching to the summaries. Okay, yep, that's all about the first case study. So we have seen the internal flow analysis to calculate the average output velocity. Now we'll concentrate on the multiple outputs. What if you have the single input and the multiple output outlets into account? So in that case, what we need to do? Okay, so here we'll consider the fluid as air instead of water, and inlet velocity I'll define as 12 meter per second. So inside pipe, normally this would be the case or scenario, we can say. Depending upon the walls, the speed might vary from 2 to 10 meter per second. Outlet is 1 atm. Fine. So these are the few boundary conditions here. Let's jump to the SolidWorks to see the same. Okay, so this is the section view of the model. So wherein this is the complete model. Okay, so I'll just activate the section view to just define each and everything. Yeah, you can analyze how exactly the cavity is made of. And now the first thing here is to define the boundary conditions with respect to flow and the nozzle as well. Lid, sorry. So to define the lids, you just need to zoom in and select the face. Accordingly, software will automatically create the lids for the outlets as well as the inlets. Okay, if you want, you can manually change by using the drop down option there. Okay, lids has been automatically created. Yeah, next step is to define the a wizard. So from here you can define the various inputs. So the unit system, keep it as it is. Analysis step internal. Here fluid will change, that is air. Remaining everything is same. I'm not gonna change anything. Okay. So accordingly the fluid domain is created. With the boundary conditions here, I'll go ahead with the instead of 12 meter per second inlet velocity, I'll select the inlet mass flow rate. Okay, I'll select the input as this lead. I'll define the inlet mass flow rate as 0.15 kg per second. Okay, so I'll select the fully developed flow, which will help me to just get the constant pressure fluid inside. So need to remember this one. So if you want to get the constant pressure, you need to activate the fully developed flow. Yeah, so the next thing is to deal with the outputs. So you can select the environmental pressure at the both the output regions, this as well as this. Okay, I'll define twice. So environmental pressure 1, and this is for second one. Once you are done with this, okay, you cannot select both the faces at once, you can delete it. Yes, I have removed one face. Now it is fine. Now I need to define the goals. I'll go ahead with the surface goals, and here you can select the pressure into account. So I'll simply define the maximum total pressure on this face and this face. Okay, and even this, there are 3 faces I have selected, so according to that you can customize your goals. Even if you want, you can add extra step, that is mass flow rate on these all the faces. Okay, so I'm gonna create the separate plots for each and every selection. So fine, so you can run the study by using the mesh option, so by refining it, or else you can directly run it by using the default settings. Again, it will take some time to just solve the whatever the input boundary condition you have given with respect to the fluid medium, and it will give the results in a fraction of time. While running the study, you can even activate the flows to cross check how exactly the flows are behaving. Okay, like this. When the results get converged, you can just have them into account. Well, in the outputs, I'm going to define the cut plot. Okay, you can change the plane accordingly. Okay, the top plane, and the contours is pressure, and you could see you can change it to velocity, and how the velocity is distributing, you could see here. So at this location the velocity is more. Once it moves towards the multiple outputs, the velocity will decrease according to the pressure distribution. When you can activate the charts and cross check how exactly the each and every goals or plots are behaving, so the total pressure and the inlet mass flow rate as well. Okay, so this is how we can deal with that particular case study. Now we'll go ahead with the one more case study, that is valve analysis. Okay, so here we'll consider the entire valve assembly into account, and we'll just slightly tilt uh, the ball valve up to certain degree Okay, and then we'll give the fluid velocity to 12 meter per second to 10 meter per second. We'll take into account accordingly, and we'll cross check the pressure drop. Okay, so why the pressure drop is utilized and why we need to calculate the pressure drop in valve industries and all, we'll see. Yep, this is the valve assembly. Okay, so you could already define the lids and all. You can activate the section view just to cross verify the same. So even I have defined the angle of attack up to certain level so that we could able to create the pressure drop region at this wall region. Okay, if the pressure drop is more, to energy needed to just maintain the same will be more. Okay, remember that. So here I have defined 110 degrees to just rotate the entire knob. Okay, so I'll start with the study now. I'll create a new wizard. We'll start with the basics. So first thing is I'll define it as pressure drop analysis 1 as a project name, and then the unit system, anyway you can change it to pressure value as bar, or remaining everything is fine. So temperature should be 10 degrees Celsius, simple as it is. So gravity can activate, you could see it is downwards. The flow is internal, no need to worry. Okay, and then finally you can go ahead with the next step. There comes with fluids. So in this I'm gonna consider the liquid. So liquid is available in fluids, and you can activate the same. The flow type is turbulent and linear. Cavitation needed, you can activate, otherwise you can keep it as it is. So default thermal wall condition, it is adiabatic here. I'm not going to change it to wall temperature as well, because here there is no changes. So thermodynamic parameters, everything is at default. The room temperature change it to 25 degrees Celsius. Okay, and finish. So software will try to analyze the fluid domain and it will create the fluid domain accordingly. And if you want to customize it by using the manual method, you can use this computational fluid domain and right click on it and edit, or else you can use these draggers to drag it accordingly. Okay, here by using the drop down, and you can define it to set or default or parametric, and accordingly you can change the dimensions or play the dimensions of the computational domain. You can hide it for now. Next thing is to define the boundary conditions. So I'll select the inlet velocity, or I'll first define the environmental pressure on this phase. So now you can define even the input velocity by just selecting the phase into account, and here the instead of mass flow or the volume flow, I can consider inlet velocity. So I'll take it as 10 meter per second, and I'll select the fully developed flow. Okay, if you want more details about it, you can go to help and just cross check, so it will help you to just cross check the same. Okay, so everything is done. You can go ahead with the meshing. So I'll go ahead with the global mesh, and I'll define the automatic refinement method to certain value. Okay, even you can do the same. And if you want to deal with the advanced options, you can use the manual method, and from there we have the different options. Okay, let's say if I switch to manual, here you can define the basic mesh along nx and y and nz directions. Here the refinement cells, you can set it to any of the level, or let's say here if I consider the minimum height of the channel refinement and the height of the maximum height, here you can define it, and according to that the channels will be created. Okay, and then the advanced refinement, here it will ask you for the small solid feature refinement. If anywhere you need, you can do it. And then here if I activate this, you could able to see how exactly the refinement will be done according to the channels. Okay, well, I'm not going to consider this much refined mesh for this. I'll just go ahead with the normal automated mesh. So I had already ran the study, so what I'll do is I'll simply, instead of running the study, I'll switch to the first case study, and here I'll switch to the results, and I'll just cross verify all the plots. For that, I would like to just showcase the goals which I have defined. The first one is the mass flow rate goal. So how much is the mass flow rate is happening with respect to the global goal condition, and then we have the global goal condition of average velocity inside the model, and the inlet total pressure. Very important step. If you want to find out the pressure drop, you need to select the phase, and here you need to select the total pressure. Okay, if you're confused here, I'll showcase again. Go to goals, right click and select the surface goals and define the phase which you want to define, and from there you just choose the maximum total pressure. Okay, and even you can select the phases and just click on green check, like that you can do it. Same thing for outlet pressure. I have selected the 1 bar and pressure drop. So for that you need to create the equation, that is inlet pressure minus outlet pressure, which is equal to whatever the value comes, pressure drop. Okay, expression you can consider, and from here I'll just choose the initial pressure minus output pressure, that is inlet total pressure to the outlet pressure. So according to the that the equation plot will be created, and once you run this we have the results. So I'll just activate this cut plot. Yeah, here you could see the results. So how the plot is uh, showing the results. You could see it is minimum is 0 and maximum 68, and you can even animate it. You could see the animation of that particular plot with respect to the position. You can stop it and you can switch to the other plots by using the velocity drop down and switching to the pressure drop down. You could see how exactly it is changing. So at the initial position the velocity is very less, the pressure is very more. Pressure and velocity are inversely proportional. Okay, so let me just see the sketch here, which I have simply drawn it at the ball wall location so that I can show you the xy plot from here to here how the pressure and velocity is changing. To do that, again switch to the xy plots from the flow simulation drop down, and here you can define the same line, and here you can select the parameters which you are looking for. Let's say if I am looking for the pressure and the velocity, you can activate the both and see here the plots. Initially the pressure is at high level, so constant pressure we have given, right, the fully developed one. So from there it will start decreasing again at the center of the wall, so it will start increase, and then finally while going out the pressure will totally decrease and velocity will increase, inversely proportional, right? The same thing here, the velocity initially at a certain velocity, and then it will try to decrease at this pressure drop reference, and then again it will increase due to the nozzle activities, and the velocity will be more at that region. Okay, so this is how you can generate the plots and the pressure drop results. And again here the flow trajectories, you can select the inlet as a reference and you can see the same. Let's say this is the phase which I need to consider into account. I need the arrows instead of pipes. Okay, once the float is generated, you can hide unnecessary float. I'll choose to velocity float, so accordingly the float pressure like this flow trajectories will also change. Okay, you can even see the animation. So I'll hide this for now. Okay, good to see. So this is how the flow is happening inside the wall. So depending upon the different angle of attack, the pressure drop will even change. So to just avoid the explosion or failure, you can just customize your entire the wall region by using the washers or something else. Okay, fine. So for the better understanding, you can even activate the assembly and you can change the transparency to see the results. Okay, this is also one of the best option. You can even activate the different views by just pressing the N, normal to view, and you can visualize the same the flow streamlines. Okay, so that's all about this session. So we have gone through the basics of internal flow analysis. We have covered the how to cross check the average velocities of at the outputs, and we have seen the multiple pressure differences at by using the multiple output model, and we have seen the pressure drop analysis by using the ball valve into consideration. Okay, so here you could see the values, the output, that is pressure drop value, it is in bars. Okay, the maximum is 11.81. Okay, inlet minus outlet pressure. If I activate the history, here you could see how exactly they are changing and how they are converging. Okay, so these charts will highly important to just deal with this kind of iterative methods to understand how the results are varying with respect to time and the iterations. Okay, fine then. So that's all about this session. Thank you guys. Keep supporting. Keep helping us to just create the new contents by subscribing or commenting. If you're extra, like if you're looking for something else, or if something goes wrong, you can even mention the same. Okay, well, thank you, stay tuned.